Problem 49. Here we have a pack of mass M is attached to a cord passing through a small hole in a frictionless horizontal plane. The pack is initially orbiting with speed v initial in a circle of radius r initial. This is the trajectory initial of the pack. The cord is then slowly pulled from below. We pull down the cord to get a new trajectory of the pack on the surface. This is the new trajectory of the pack with a radius equals to r. So we have initial state and we have a final state. Initially we have v initial and with a radius r initial, and finally we have v final. Let's say we have finally v and radius r, initial and final. I ask you what is the speed of the pack, then the radius is r. No, what is the speed of the pack when the radius is r? So I want to find v. Okay, as you see here, summation of tau external equals to dl divided by dt equals to 0. Why? Because here the external f here, first of all we have a system of mass m, we have a mass m and we have a cord. What is the external f applied on the system? Here we have the weight is down, we have the reaction is up, and here the tension is not external, the tension is internal F. We don't talk about the internal F. And here the tension is internal. So we have N, we have mg, and we have two internal, and that's all. You see here N and mg don't contribute to the torque. mg and N will not rotate the pack on the plane. We can say here N and mg do not contribute to the torque. Anyway, you see here N is parallel to the axis and mg is parallel to the axis. When the force is parallel to the axis, it doesn't have any effect and it doesn't have tau. So we can say tau of N plus tau of mg equal to 0. This is the summation. This is the summation of tau external. So equals to dl divided by dt. In this case, we can say L is constant and the system is isolated system. In this case, we can say we have a conservation of angular momentum. L initial equals to L final. Okay. Initially, we have, here we have a pure rotational motion. we can apply directly the relation here as you like. You can apply in general L equals to I omega, or you can apply L equals to R mv. This is in function of omega and I, and this is in function of R and V. As I want to calculate V, so it's better to put the value of L in terms of R, M, and V. So we can say here initially we have R initial times M times V initial. This is the initial L. And as the final state, we have R, we have M, and we have V. When the system has a new trajectory, we have a new velocity V, and we have a new radius R. So L in this case equals to R mv. I want to calculate V, which is equal to V equals to R initial divided by R times V initial. This is the value of V in terms of the initial velocity. This is part 1. Part B. Find the tension in the cord as a function of R. We have to find the tension in terms of R, in function of R. How much? You know here we have the tension in toward the center. Okay, we have the tension T. Here, as you know, we have a circular motion. We can put it like this. Here we have the velocity V, and also we have a tangent. And here we have T. You know, we have T, and also we have a radial. This one is T. We have a radial, and here we have a tangent, and we have the velocity V. And you know, E tangent unit vector is like this, and here we have E radial must be out. So we have E radial, and here we have E tangent. We can apply Newton's law. What we have mg down, and up we have n. Okay, it's not in the direction of E tangent and E normal. I want to calculate T, so we can do the projection in terms of E R. In this direction of ER, we have only the tension T. We don't have any other force applied on the object. So we can say T, you know here, T is opposite to ER. We can say T as magnitude times minus ER. Okay? Which is equal to AR is opposite to ER. So we can say minus V square divided by R, and we have M. Don't forget M. MA times ER. So we can write T or T equals to V square divided by R times M. I want to calculate T. Here we have, I want to calculate T as a function of R. Okay? This is the value of T in function of R. We can substitute the value of V. We can write, because here we have V in the function. We have to put V in terms of V initial and R initial. So we can put V square here from here. Okay, V square and here square. We get R times M, and V square equals to RI square times V initial square divided by R square. So T equals to M times R initial V initial square divided by R cube. This is the value of T. Part C. How much work omega is done in moving from R initial to R final? I need to find the work consumed by moving from this position to the final position. You know, we have work kinetic energy theorem. The work done equals to delta kinetic energy, which is equal to kinetic final minus kinetic initial. We have a rotational motion, circular motion, so we have I over 2 omega omega final square minus I over 2 omega initial square. We can write like this, or we can write like this: M over 2 V final square minus M over 2 V initial square. Why? Because here, let's say the kinetic energy final equals to I over 2 omega final square. You know, I of the mass M equals to ICM plus MD square. We don't have ICM because the axe is not passing through the mass M. So we have only M times R square. This is I divided by 2 times omega. We have a relation between omega and V, where omega equals to V divided by R. Omega square equals to V square divided by R square. So here we get M divided by 2 V square. Okay? So we can put I over 2 M omega V square, omega square, or we can write M over 2 V final square. It's the same. And also about the kinetic initial, we can write I over 2 omega I square or M over 2 V initial square. Here we can write omega equals to M over 2 V final square equals to R initial divided by R times V initial square minus M over 2 times V initial square. We can put outside have M V initial square. We get inside R initial square divided by R square minus 1. This is the value of the work done, consumed to move the object from this point to this point.